Let's look at random events occurring on the timeline leading to failure of an item in some detail. So let's say that we have a component which has some reserve strength and it can withstand some shocks, not fail at the first shock itself, and these shocks occur according to a Poisson process. So this component fails at shock number k. We did look at the Poisson process briefly when we discussed joint distributions. So this is a revisit to Poisson processes. The failure time would be the sum of all these interarrival times. So if failure occurs at shock number k, the time is built up with increments delta t1, delta t2, all the way up to delta tk. Each such increment is the interarrival time between successive shocks. So pictorially speaking, this is what we have. We start from 0, and then after delta t1, the first shock occurs, so that's at random time t1. Then after random time delta t2, after random interval delta t2, the second shock occurs at random time t2, and so on until we reach the kth shock occurring at tk. So we know that in a Poisson process, the interarrival times are exponentially distributed with the rate lambda, and they are mutually independent. So that's a very useful and very powerful property. And to reiterate that, so all the delta t's are exponential with the same constant lambda, which is the rate of the Poisson process, and they are mutually independent in disjoint intervals. So the failure time, so the sum of these independent exponentials is a gamma random variable, and tk is gamma distributed. The gamma distribution is defined by two parameters, k and lambda. So and if k is an integer, it's sometimes known as the Erlang distribution. Now let's derive the CDF of the gamma random variable. So by definition, the CDF of tk evaluated at small t is that the shock number k occurs at time t or earlier. So the probability of that event, which we can restate as the probability that at least k shocks occur in the interval 0 to t. And if we take the complement, it's 1 minus the probability that up to k minus 1 shocks occur in interval 0 to t. So 0 shock or 1 shock or 2 all the way up to k minus 1 shocks can occur in the interval 0 to t. So 1 minus the probability of that would give me the CDF of the failure time tk. Now there's also a very useful result comes out of the Poisson process, is the number of events in a Poisson process over time 0 to t is actually a Poisson random variable. And we have seen the Poisson random variable extensively when we discussed the common distribution functions. So we should be able to use the Poisson PMF and the Poisson CDF. So that x shocks occurs in interval 0 to t, we know the PMF, it's lambda t to the power x over x factorial times exponential of minus lambda t. The lambda is the same lambda that defines the Poisson process. So we need to add x from 0 to k minus 1 and subtract that sum from 1. That would give me the gamma or more specifically the Erlang CDF. And its mean and variance could be defined in terms of k and lambda, and that's what we have here. The mean is k over lambda and the variance is k over lambda squared. Now, continuing, the gamma distribution is closed under addition, the gamma family, provided the rate does not change. So if we continue adding gammas from the same underlying process defined by lambda, then gamma k1 lambda and gamma k2 lambda, if they're independent, then their sum would be a new gamma random variable with parameter k1 plus k2 and the same lambda as before. So now let's solve one or two examples with this sort of arrival on the time axis.